Good afternoon, dear students. Today we are going to discuss a topic which is very popular in quantum mechanics, and that is about the quantum harmonic oscillator, and this is the part 2 of the lectures. Previously, few days before, I took this class regarding this, and that was the quantum harmonic oscillator part 1. So, this is considered to be a continuation of that particular lecture. So, this is the part 2 of that, and you know the quantum harmonic oscillator is a important topic regarding the quantum mechanics syllabus, which is included in our university, that is West Bengal State University, in semester 5, and in that contest going to discuss few aspects of say quantum harmonic oscillator, but in a different way rather than the procedures that had been adopted in the earlier lectures. Oh, okay. Let me give you my introductions. I am Amitava Bhaduri, the assistant professor in physics in the physics department of this college. And as I already mentioned, that the topic of discussions that we are going to discuss is about the quantum harmonic oscillator, and this is a separate method of dealing these situations. This method is referred as the operator methods, because this method is slightly different from the earlier methods which was adopted in my previous these lectures, and that method was based on Schrodinger's approach. But this is a method which is exclusively depends on the that is the operators. So, we are not going to follow the Schrodinger's wave equations while dealing with this situation. This is basically the quantum harmonic oscillators problem and dealt with operators methods. Now, in the introductions, we see in our earlier discussions relating to quantum harmonic oscillators, as I already mentioned, it was the Schrodinger's methods, and in that particular methods we applied the Schrodinger's wave equations and then solved the Schrodinger's equations, and then we obtained the energy eigenvalues and eigenfunctions of the quantum harmonic oscillators, and we found that the energies of the quantum oscillator was quantized, and the expression for the energy looks like that. En that is equal to h cut omega n plus half, where the n is the quantum number, and at the same time also we found the different probables eigenfunction related to these quantum harmonic oscillators. So, that was the content part of the previous lectures, and here the outcome of this particular discussion will be same as it was in the earlier occasions, but the method, as I already mentioned, that this is slightly different from the methods that we adopted earlier. Now, so the method actually started from these portions here. Now, here you see this is basically the Hamiltonians of the one dimensional harmonic oscillators. Mass of the oscillator is considered to be small m, and you see the omega, that is the, you can say, the natural frequency of the oscillator, and x is the displacement of the oscillator from its point of equilibrium. And here the p, that is the momentums of the oscillators. Now, if we consider all these physical quantities, then in that case the Hamiltonians of these systems can be written as p square by 2m plus half of m omega square and x square. So, that is the Hamiltonians of the quantum oscillators, and we considered here the quantum oscillators for the one dimensional case, but I must say that the same concepts can be extended for three dimensional harmonic oscillator, but that is a separate approach, and I am not going to discuss that approach here. After that, what we see that there are two important physical quantities involved in the expression for these Hamiltonians. One is this p, that is the momentums of the quantum oscillator, and the second one, that is the x. X is the another physical quantity, that is the displacement of the quantum oscillators, and this x and p, they have their respective operators, and their respective operators is going to follow this type of commutation relations, x comma p, that is equal to I into this h cut, and as we know this is is the standard result of the quantum mechanics, where x and the p operator, they have a commutation relation that is given by this equations numbers 2. So, we have the equation number 1 which expresses the Hamiltonians of the system, and the equation number 2 is going to represent the commutation relation between x and p. Now, here with the help of x and p, these two are the two operators, and we are going to construct two individual operators here. One is called small a, another that is called a dagger. Here you see a plus sign, but this plus sign in the language of quantum mechanics, it is referred as dagger. So, a is one operator and a dagger is the one operator, a dagger is another operator. Now, these two operators, that is basically the centerpiece of this entire approach. Now, you see the name of the method is the operators methods. So, naturally entire method is based on operators. Which operators? These two operators, one is a and second one, that is the a daggers. Entire method is based on these two operators, and this a and this a dagger, both of these two operators can be obtained by a, you can say, a combination of your displacement operators and also the momentum operator. And if you go for a, then a can be expressed as m omega by 2 h cut, where h cut is the reduced Planck's parameter, that is equal to h by 2 pi to the power half into x plus I is the imaginary number, I square, that is equal to minus 1, so you know, and then 1 plus 2 m h cuts omega half p. So, we see x here, we also see p. So, it is nothing but a combination of x and p which resulted these operators small a. Now, if this is the expressions for a, then if you consider the complex conjugate of these expressions, then so you know that if we take a complex numbers a plus ib, the a plus ib is a complex numbers. So, if you take the complex conjugate of that, then that will turns into a minus ib. So, here suppose this is your a plus ib. So, if you take the complex conjugate, then definitely that will turns into with this minus of this, and that resulted this operators a dagger. So, you have a and you have a dagger, and both of these two operators can be represented as a combination of x and p. So, this is the most you can say the importance, you can say the initial part of these discussions. So, we introduced here the Hamiltonians and also the commutation relation between x and p, but at the same time A and A dagger, these are the two important this operator, they have also been introduced. And with this we have to do little bit of mathematical steps, and mind that here and here also we need some concept of the linear vector space and particularly the Dirac bracket notations. So, these are some concepts which are to be involved in these discussions here. So, let us see, and we will discuss this thing step by step, but before that let us have some mathematicals, you can say the relationship related to A and A daggers and and also with the Hamiltonian. If I take A this and if I take A daggers, so if I multiply both of them, then we get A into A daggers, and that looks like this: m omega by 2 h cut x square plus 1 by 2 m h cut omega, then you have p square, and then I by 2 h cut we have px minus xp. Now, this px minus xp, px minus xp, so that is basically the commutation relation between p and x. Now, here if I write that this on this board here, suppose if I take a board and if I write, suppose if I write here, if I write suppose we have x comma p, if that is equal to suppose I h cut, and then definitely if I interchange this position p comma x, if I write this one, so here there is a negative sign, that you know. So, p comma x, and this p comma x is equal to px minus xp. So, that is equal to minus of I h cut. So, here this px minus xp can be written as minus I of h cut, and therefore, h cut and h cut cancel out, I into minus out turns into half. So, therefore, so you got this one. So, A into A dagger, so that is equal to h cut by capital H by h cut omega plus half. Similarly, anybody can do A dagger into A, so that is equal to capital H by h cut omega minus of half. Good. So, we have A into A daggers, that is equal to H by h cut omega plus half. So, similarly, it can be shown by doing exact sort of these mathematical steps. A dagger into A, that should be equal to capital H by h cut omega minus half. So, we obtain A daggers and we also obtain A daggers A. And now, suppose if I add them together, if I add A daggers with A daggers A, then this minus halves will be cancelled with this plus half, and ultimately we got this expression for the Hamiltonians. So, look at this equation number 7. So, Hamiltonian is nothing but also operators, and these operators can be expressed as a combination of A and A daggers. After that, we have A daggers and we have A daggers A. So, with the help of this and this particular equations, we can easily find out the commutation relation between A and A daggers. So, that is also very important regarding this particular discussions here. That means, once I introduced A daggers and A daggers A, then naturally if I subtract A daggers A from A daggers, so that will give me A comma A daggers, that is the commutation relation, and that is happens to be equal to 1. So, that is the equations numbers 8. So, we started from equations 1, 2, 3, 4, 5, 6, 7 and we are here. Now, A daggers commutation relation, that is equal to 1. After that, you see here this is another commutation relations where A operators and capital H operators are involved. Capital H operators can be obtained from here using equation number 7. So, if I use the commutation relations between A and A daggers, so then exactly what I can write, A into capital H minus capital H into A. So, we have A, and in place of capital H you can write this enter. So, you are writing this one minus H into A, your H is this one, this is your H, and that is followed by A. So, this is your H and this one is A. So, this is basically the commutation relationship between A and H, and from here see A multiplied with A dagger give rise to A square A dagger, and here it is A daggers A minus of, and here also you see A daggers A. So, A daggers A and A daggers A will be cancelled out, and finally you got this result. This is about A square into A dagger. Now, this A square into A dagger commutation relations, if we follow the commutation algebra that is given in any standard book of quantum mechanics, then A square A daggers, these commutation relations can be written in this way: A into A daggers plus A into A daggers A. Now, as we obtained A dagger, that is equal to 1. So, here so you can write A into 1 plus 1 into A. So, therefore, you will get 2A, and these 2 and these 2 cancel out. So, ultimately you got H cut omega A. So, basically the commutation relation between A and capital H turns out to be equal to H cut omega A. So, this is another important relation involved with this discussion. Now, this is derived in this way. At the same time, similarly, it can be shown that if I replace these A operators with A dagger operators, so then I got the commutation relation between A daggers and H, and if you put A daggers and H, so then the result will be minus H cut omega A dagger. So, this is one result, and this is another result. So, in the first page, if you see, you can get totals 10 equations, and for each and every equation give you some importance, you can say the relationship. In the subsequent portions of the today's discussions, we are going to utilize all this relationship in order to expand our discussion, so that we can get the ultimate result. So, the first page of this total write up is entirely dedicated to just give rise to the frameworks which is essentials for the overall discussion, which can lead us to the final result. So, now come back to the second page. So, let us see what is there. In the second page, it started from this concept here. In the second page, it started from this concept. Now, here the concept is taken from the linear vector space, and we can say that it is the concept with the Dirac's bracket notations. So, in that case, you can psi m, and here is the psi n. So, these two are, you can say, some eigen Kate's vectors. This one is the bra vectors here, this is the Kate vector, and H, that is the Hamiltonians. So, if we carefully observe the Dirac bracket notations, which is highly needed in this particular topic. So, the knowledge of Dirac bracket notation is needed. So, if you follow the Dirac bracket notation, then psi m H psi n's, this can be written as the psi m and H psi n. Now, you see the H psi n is equal to E n psi n. So, therefore, whenever H psi n is there, so that is giving you E n psi n. So, that E n will be placed in the real space. So, if you remove the ENs, En will automatically come here as it is here, and then you are left with psi m and psi n. We left with the psi m and psi n. Now, this is your En. Now, Dirac bracket notation or Dirac bracket algebra is giving us that whenever we are having this sort of situation, that means this is the, you can say the scalar product between psi m and psi n, that is called the inner product in the linear vector space. So, that will actually resulted the Kronecker delta functions. So, that means psi m psi n, that is equal to delta mn, and you know for the Kronecker delta functions we have only the two values. If m is equal to n, so then that will give us 1, but if m is not equal to n, so that will definitely give us 0. So, we started with this, and at the end of our journey we obtained En delta mn. So, that is the equations numbers 11. Now, where En is considered to be the energy eigenvalues of the nth state. Remember, for any quantum state we have different energy eigenvalues, and these values are discrete values, and related to each and every energy eigenvalues there may be some energy eigenfunctions. So, considering the nth state, these are called different quantum state. So, if I consider the nth quantum state, then its corresponding energy eigenvalue is given by En. So, that means the En that we are seeing here, that is nothing but the energy eigenvalues related to the nth quantum state. Next, we shall evaluate the matrix element. What is the matrix element? See, here the operator is H. Now, we are removing this operator H and we are placing A dagger A. So, if I place A daggers A, then A daggers A, if we see the first page, you can find A dagger A, that is equal to H by H cut omega minus half psi n. And from here, the result is like this, psi m H psi n. Psi m H psi n will give you see the En psi m psi n. So, therefore, this is En H cut omega minus half psi n, and here also this is psi m and this is psi n. So, if we follow this step, that is psi m H cut omega minus half psi n, that is actually giving you En H cut omega minus half psi m psi n, and in place of psi m psi n, as before we put Kronecker delta. So, here also we can put Kronecker delta, that is delta m comma n. Now, as I already mentioned that it has two value, either you can put m equal to n, and for that the value of Kronecker delta is equal to 1. So, put m equal to n. So, in that case this will be 1 and we will get En minus H cut omega minus half, but in the left hand side you have to put m equal to n, because the moment you put m equal to n, so you have to put m equal to n from both sides of the equation, and the right side you have Kronecker delta m n. So, if you put m equal to n, this is turns out to be equal to 1. So, you are getting En minus H cut omega minus half in the right hand side of this equation, and the left hand side of the equation this should be psi n. So, therefore, we got this result, psi n A daggers A psi n is equal to En H cut omega minus half, that is equation number 12. Now, this matrix elements which is represented by equation number 12 can be calculated in some other different way following the rules of linear vector space or the Dirac bracket notations. Look at here, psi n A daggers A psi n can be written in this way, psi n A dagger psi m A psi n. So, psi this, if you exchange this one psi, bring this one here and this one this, then A dagger will be changed into A. So, these are the rules of, you can say, the linear vector space, followed by there should be dagger sign. So, that means this and this they are equal. Similarly, this is psi m A psi n, here also psi m A psi n. So, following these steps which comes from here, what we are doing? We are simply exchanging m and n. The moment we are exchanging m and n, you can find this dagger sign will come here and this will become A. After that, psi m A, psi n, this dagger, psi m A, psi n dagger. So, you know that A star into A is A mod square. So, similarly, this is a, suppose if we consider this to be complex numbers, this is the complex conjugate of this numbers and this is the complex numbers here. So, the product of complex conjugate with the complex numbers will give you the mod sign here. So, definitely this will be the mod here, and you know any mod sign, mod square, definitely that should be a positive quantity. So, this should be always greater than 0, and that is the, you can say, the significance of equation number 3. So, we got two values of the same matrix elements. One is represented by equation number 12 and the second one is represented by equation number 13. After that, let us see what is coming out. Okay. Say, are coming out. So, for this one. So, if we compare their left hand sides of these two equations, then we find they are equal. So, the right hand side must also be equal. So, the right hand side of the previous equation was this and the right hand side of this equation is this one. So, this should be greater than 0. So, this should be definitely greater than 0, and obviously in that case En by h cat omega should be greater or equal to half, and ultimately you got this result. That is the equation number 14. This is quite interesting result. This result is telling us the physical fact regarding this quantum system is that if I consider that En is the energy eigenvalue of the nth quantum state, then this energy eigenvalue should always be positive. That is the first aspect of this equation number 4. This never be negative. Energy eigenvalues of the quantum system pertaining this quantum oscillator should always be positive, which is very much reflected by this equation number 14. Second thing is that energy eigenvalues are discrete. So many energy eigenvalues are possible, but the least value should always be h cat omega by 2. All the values which are permissibles under this quantum system should be always greater than h cat omega by 2. This is the least value, and all the other value should always be greater than h cat omega by 2, maybe 3 h cat omega by 2 or 5 h cat by omega by 2. So, these are the permissible values of the En. I mean to say that quantum system pertaining this type of oscillator has energy eigenvalues which is either equal to h cat omega by 2 or it is greater than. So, the lowest value of the energy eigenvalue, that should be equal to h cat omega by 2. You cannot find any energy eigenvalue which is less than h cat omega by 2. So, that is the very important consequence of equations number 14. After that, you can write the Schrodinger's equation, and according to the Schrodinger's equation in Dirac's bracket space, we have h psi n is equal to n psi n, where psi n, that is the eigenkette, and which is going to represent the nth eigenkettes here. So, h psi n, that is equal to n psi n. Now, here operating from left by A. So, that means you are taking the operator A and try to operate the operator A on this equation, but from the left side. So, bring A here. The moment you bring A here, so you can write A h psi n, you have to bring A here also. So, that exactly that we are seeing here, that means A h psi n, A En psi n. So, I bring operator A and I operate the operator A on both sides of the equation, left hand side as well as the right hand side. If I do so, in that case we also know, we know the commutation relation between A and H, and from that commutation relation AH is equal to HA plus of H cut omega A. That is the result which we obtained in page numbers 1. So, from there you can take AH is equal to HA plus H cut omega A. So, in place of AH put this one HA plus of H cut omega A psi n A psi n. Slight rearrangements will give you H A psi n En minus H cut omega A psi n. That is the equation number 15. Let me scroll it. Now, say, so we got here H A psi n, that is equal to En minus H cut omega A psi n. Now, if we compare this equation 15 with the earlier equations as the equation number Schrodinger's equation, in the case of the Schrodinger's equation it was H psi n equal to En psi n, but here H A psi n that is equal to En H cut omega A psi n. Now, the physical significance, physical equals the mathematical significance which is coming out from here, and that is quite interesting. You see, if we carefully observe this equation 15, then it is understand that as if En be the eigenvalue of Hamiltonian corresponding to the eigenstate psi n, if En is the eigenvalue for the Hamiltonians for the eigenstate psi n, then A psi n is the eigenstate of the same Hamiltonian's operator, but with eigenvalue lowered by H cut omega. What is the meaning? See, if I write H psi n, I have to write En psi n. But H psi n ket, I have to write En psi n ket. But whenever I write A psi n, H A psi n, in that case the right answer of this equation is En minus H cut omega. So, as if it appears that for these equations, that is the equation number 15, which is considered as the eigenvalue equation of the Hamiltonian operator, A into psi n is just simply behaving like an eigenket for the Hamiltonian H, and if it is the case, that means A into psi n is the eigenket for the Hamiltonian operator, then its corresponding eigenvalue will be En minus H cut omega. So, previous eigenvalue was En, now it is reduced by H cut omega. So, why it is reduced? Because now we bring the operator A over the function psi n. So, when I operate A over psi n, then for the same Hamiltonians, eigenvalues reduced by H cut omega. So, that is why this operator, that is called destruction operator. Why destruction? Because the moment I operate A over psi n for this Hamiltonian H, that will actually brings the eigenvalue of this Hamiltonian operator, which was previously En, now it turns into En minus H cut omega. So, it is reduced the eigenvalue by H cut omega unit. Now, with the same continuations, if I use this operator twice, here we are using the operator single times. Suppose we operate this operator twice, then we are having A into A square. If you have A square psi n, so that means you are using the operator small a twice. In that case, then the eigenvalue will be reduced by 2 units. Previously it was En, now it will become En minus 2 into H cut omega. Look at 2 into H cut omega, and here also A square psi n ket. H A cube psi n ket is equal to En minus 3 H cut omega A cube psi n's gate. Following this one, if we apply small a operator for the nth time, then it will become a to the power n psi n gate, that is equal to E n minus n h cut omega a n psi n. So, if we carefully observe this, if we study these sentences, then one thing that is clear, that the significance of the operator small a is come into the pictures, which actually convince us to understand that here the role of small a operator is to destruct the eigenvalues of the Hamiltonians. If I use it for a single time, it will reduce the eigenvalues by h cut omega unit. If I use it for the 2 times, then the reduction will be 2 into h cut omega. For the 3 times, it will be 3 into h cut omega. For the n times, it will be n into h cut omega. And that is the reasons that in all the standard book of this quantum mechanics, these operators A has been referred as either annihilation operators, which can destroy something. Here it is actually destroying the eigenvalues of the Hamiltonians. So, therefore, this is called the destruction operators or the annihilation operators. On the other hand, interesting fact about the other operators is that, look at here the other operators, see exactly in the similar way, instead of taking h a psi n's, if I take h a dagger psi n, previously you took a, so you got h a psi n skate, but now suppose do not take a, you take h a dagger psi n's, like this one, h a dagger psi n. You know the commutational relation between a daggers and h in the first page. From there, anybody can calculate that h a dagger psi n's will give you E n plus h cut omega. So, here what we are saying, a dagger operator is going to increase the eigenvalue of this Hamiltonian, which was previously E n, now it has become E n plus h cut omega. So, if you use a dagger operator single time, so that will raise the eigenvalues by a unit, and that is equal to h cut omega. If you use it for the 2 times, that means a dagger square. So, in that case it will raise the eigenvalues of the Hamiltonians from E n to E n plus 2 h cut omega. So, the 2 unit, that is the reason that a daggers operator has been referred as creation operators. It is called the creation operators. A was annihilation operator, but this is called the creation operators. It can create eigenvalues, or it is also referred as the raising operator. That one is called the destructions or the annihilation operator, or lowering operator. This is called the raising operator or the creation the creation operator. So, it can create the energy eigenvalues. Okay. Thus, the operation of a dagger raising the eigenvalue by h cut omega, hence called the raising operator. So, let me just scroll it down. So, we discussed here the role of operator A, which is called the annihilation operator, destruction operator, because that is going to lower down the energy eigenvalues for the Hamiltonian operators, and also the A daggers, whose main role is to raise the energy eigenvalues by unit h cut omega. So, therefore, this is called raising operators or the creation operators. After that, let us have a discussions of the ground state of this quantum system. Ground state means it is the lowest possible state, and the corresponding energy of this lowest possible state is called the ground state energy. For each and every quantum system, the lowest permissible energy is considered as the ground state energy, and this particular system is also not having any exception. So, here also we are expecting a minimum quantum energy for the system, but that is called the ground state energy. So, let us have a discussions on how to calculate the ground state energy for this quantum oscillators. That you see, denoting the ground state eigens kate corresponding to the minimum eigenvalues, that is, suppose your ground state energy, that is E0. E0 is the lowest energy. You cannot have any energy below of that. E0 is the lowest, and that is considered to be the ground state energy. And this E0, this ground state energy is E0, and its corresponding eigenstate is given by psi 0. So, therefore, what you can write? H A psi 0, that is equal to E0 minus h cut omega. Why? Because whenever we write H A psi n, in that case it was En, it was En. Now, it is H A psi 0. So, here n should be 0. So, you can write E0 minus h cut omega A psi 0. Now, here En, which is the, you can say the energy eigenvalues for the nth state, it should always be greater than h cut omega by 2. It is always greater than h cut omega by 2, and this equation is possible only if A psi this psi 0 kate is equal to 0, and this is the clear understanding here. You see, this one is the lowest possible quantum state. So, if we apply A, that the destruction operator, so destruction operator will always try to bring down the its corresponding energy eigenvalue, which was considered E0, and it will always try to lower it down below of E0, but you already considered that E0 is the bottom line. E0 is the bottom line of this quantum system. You cannot imagine any energy which is below of that E0. So, you do not have any energy which is below of this E0. E0 is the ground state energy. So, any energy below of that E0 is not possible, and if that is not possible, you cannot ignore the influence of A. So, therefore, whenever the A is operating over psi 0, so that should give you the result, that is 0. So, A psi 0 should be 0, because you cannot go down below of psi 0. Psi 0 is your bottom line, E0 is your bottom line. If you apply A is having a tendency to bring it down of psi 0, that is not possible. So, A psi 0 should be 0. Now, if we multiply both sides by A dagger, so A dagger A psi 0 is 0, and A dagger A is equal to this. So, this psi 0 equal to 0. Now, H psi 0 is equal to capital E psi 0. So, therefore, capital E0 psi 0. So, H psi 0 is equal to capital E0 psi 0. So, therefore, these relations will actually give you E0 h cut omega minus half of psi 0 kates. Now, the thing is that you cannot put psi 0 kate to be equal to 0, that is not possible, because you consider that the psi 0 kate, that is the lowest possible quantum state, it exists. It exists. Under no circumstance we can claim that psi 0 kate is equal to 0. If I put psi 0 kate equal to 0, that means the psi 0 kate never exists at all, but we already considered that the psi 0 kate is our ground state wave functions. So, under no circumstance you can claim that the psi 0 kate that is equal to 0, but the right hand side is 0. So, how you can reconcile these situations? You cannot make this to be equal to 0. So, you have only a single option to put this factor should be equal to 0. So, that is you can do. So, E0 by h cut omega minus half, that should be equal to 0, which brings you E0 is equal to h cut omega by 2. So, in this way the lowest possible energy of these quantum systems can be obtained. This is referred as the 0 point energy. Previously, in my first lectures, which was entitled at the quantum harmonic oscillator part 1, and we discussed the Schrodinger's methods, and in that methods we calculated the 0 point energy of this quantum harmonic oscillator system, and we found the expression for 0 point energy was half h cut omega, and here also we are getting the same 0 point energy, which is E0 is equal to h half h cut omega. So, this particular result is totally tallied with the result which we obtained in the earlier occasions. So, that is the big success of this theory, which is based on the operator methods. After that, see, so E0 appears as the 0 point energy. So, in this system, so this is the lowest possible energy. You cannot expect any energy which can go below of this. After that, you know this H A dagger psi 0 is equal to E0 H cut omega A dagger psi 0, which is previously we discussed this one. So, therefore, so A dagger H psi 0 is equal to E0 H cut omega. So, E0 is equal to H cut omega by 2. So, this becomes 3 by 2 H cut omega. So, therefore, what we see that if I apply A dagger operators over psi 0, so that will actually boost the energy eigenvalues by an unit of H cut omega. So, which resulted the next eigenvalues available is E0 H cut omega if I bring A dagger operator for a single time. So, the next eigenvalues I got, that is 3 by 2 H cut omega. So, I started with half H cut omega, but next eigenvalues, which is the permissible eigenvalue, that is will be 3 by 2 H cut omega. If I apply this A dagger operator twice, so in that case it will become E0 plus 2 H cut omega. So, that will actually give us the next energy eigenvalue, which is 5 by 2 H cut omega. So, I mean to say that by applying A dagger successively, you can create more energy values. You have started your journey from E0, which is half H cut omega, but next eigenvalue will be 3 by 2 H cut omega by using an A dagger operator for a single time. If we use the A dagger operator for 2 times, that will give you 5 by 2 H cut omega, 3 times that will give you 7 by 2 H cut omega. So, these are all possible eigenvalues of the Hamiltonian operator under this system. So, if you apply this A dagger operator for n time, if we apply the A dagger operator for n time, that means H A dagger to the power n, then this will become E0 plus small n H cut omega, because now this energy become E0 plus n H cut omega. And what is E0 plus n H cut omega? E0 is equal to H cut omega by 2 plus n H cut omega. That will actually give you this result, n plus half H cut omega. So, this one is what? This is the energy eigenvalue for the nth quantum state. So, let me repeat it again. We started our journey from E0 and successively we are going to apply the A dagger. Single time it will give us 3 by 2 H cut omega t. For 2 times it will give us 5 by 2 H cut omega. For n times it will give us n plus half H cut omega, and this is referred as the energy eigenvalue for the nth state. Now, energy eigenvalue for the nth state for this quantum oscillator system is given by equation number 19, which is exactly equals with the same expressions we got in my previous Schrodinger's methods. In that case also En was n plus half H cut omega. Now, so this is the energy eigenvalues, this is the energy eigenvalues for the quantum oscillators. Putting the different value of n's, you can get the associated value of, you can say, the En. And the series of eigengates, because for any quantum system we have eigenvalues and the eigengates. Eigenvalues will be given by this. Depending upon the different value of n, you are having different En eigenvalues of Hamiltonian operator. But at the same time, what are the different eigengates for the same Hamiltonian operator? The first eigengate is this psi 0. ground state wave functions you can say. The next eigengates will be A dagger psi 0, next will be A dagger square psi 0 gate, next A dagger to the power 3 psi 0, and the last one A dagger, that is to the power n psi 0, and this one is nothing but psi n gate. This is nothing but psi 3 gate. In this way the different, you can say, the wave functions you can obtain. Now the different eigengates, how you can obtain different eigengates, we are at the last end of our discussions. So this is the last page, okay, this is the last page here. How the different eigengates can be obtained. A very small discussions we have here. See, different eigengates. We have A is equal to this, we can write 1 by 2 m h cut omega half, and then we have m omega x, and we put the actually the expression for the momentum operators in quantum mechanics, and if we do so, in that case we get h cut del x operator. Similarly, A daggers can be represented by minus h cut del x operators. So this is the expression for A and A daggers. Now take this one, A psi 0 is equal to 0, that's we already considered, A psi 0 that's equal to 0. So in place of A you can bring these operators right here. In place of A you can put these operators, this operator psi 0 that's equal to 0. So d psi 0 is equal to minus m omega x by h cut dx. Now if we integrate this one, that will give you psi 0 is equal to n 0 e to the power minus m omega x squared by 2 h cuts. Okay. So this is the expression for the psi 0, where the n 0 is a constant parameters, you know. So psi 0 now turns out to the exponential functions. The once you know the expression for the psi 0, which is reflected in equation number 20, now so you can obtain the value of psi 1. It is very easy to obtain. Psi 1 is equal to A dagger psi 0. If you really want to find out the expression for the psi 2, that's also you can do. Psi 2 is equal to A dagger square psi 0. Psi 3 will be equal to A dagger cube psi 0. So similarly, if you are interested to find out the expression for the psi n, so you can do psi n is equal to A dagger to the power n into psi 0. So that's you can do here. So psi 1 is equal to n1, this is your A daggers into psi 0 here. Similarly, if you are interested to find out the psi 2, you can do psi 2 equal to n2, bring it n2 and then write m omega x minus h cut del x square, make it square, because A dagger square is needed in order to get the that is the psi 2. So make it m omega x minus h cut del x to the power 2 e to the power minus m omega x square. So if you do this one, you will get the expression for psi 1. So you started your journey with psi 0. Psi 0 is called the ground state wave function, psi 1 is the first excited state wave function. If you are interested, you can obtain psi 2, you can obtain psi 3, you can obtain psi 4. In this way, if you are interested, you can obtain the psi n, which is the you can say the wave function for the nth state. So therefore, this particular expressions that we got here in the form of psi n is exactly tallying with the expressions that we had in the earlier occasions, where you use the Schrodinger's methods to obtain the expression for the nth you can say the wave functions for this quantum oscillator. So in this way, this elegant method, without doing any differential equation, without considering any differential equation, without solving any differential equations, without considering the you can say the Schrodinger's equations in its well known form, we come to the conclusions which is exactly same as being done in the Schrodinger's methods. And with that, we can understand the elegancy of this particular methods, which is really very elegant, and here the scope of mathematics is not so sound as comparables with the earlier one, and the student find it very simple to understand. So, if you follow it, definitely you can see that this method will be much more attractive and very easy to understand. And with that, I am going to conclude my today's speech, and thank you all of you.